Okay, let's talk about changes in internal energy, delta E. The internal energy is the energy contained within a substance. That includes kinetic, potential, gravitational, electromagnetic, whatever kind of energy it is. Another statement of the first law of thermodynamics says that the change in energy is determined by the heat flow and the work. So delta E, since it's a state function, is equal to the energy of the products minus the energy of the reactants. Or the change in the delta E is equal to the heat plus the work. Now, if the heat is positive, the heat's going into the system. If the heat is negative, then it's going out of the system and into the surroundings. If work is going into the system, then it's positive, and or the surroundings do work on the system is another way of saying it, or the work is negative, that means the system's doing work on the surroundings. The work's going out of the system. So delta E is negative when it's released from the system to the surroundings. And it's positive when the energy is going in net. Now, if we look at combustion of pentane plus oxygen, it's going to release 3,516 kilojoules per energy. And notice it's on the product side. So that's a negative 3,516 kilojoules for the delta E. If I take the reaction and flip it around, necessarily the number becomes positive 3,516 kilojoules. Now, what you can get out of that is you can see that burning a fuel produces a lot of energy, but making that fuel requires energy. If you wanted to make gasoline or something from carbon dioxide and water, that would be a much more complicated process requiring a catalyst to lower the energy threshold. I will link in the comments or the description of this video on what they call the Troper fish process so that you can see how that might be done backwards. So let's look at a couple of examples. If 1200 joules of heat are added to a system in a state E1, the system does 800 joules of work on its surroundings. What's the energy change for the system, delta E? All right, let's look at this problem. I've copied the information now. It's a positive 1200 joules of energy because the energy is going into the system. Negative 800 joules of work because the system is doing work on the surroundings. Past that is just simple addition. It's going to equal 1200 joules plus a negative 800 joules for a net positive 400 joules of net energy going into the system. So in most chemical or physical changes, the only kind of work is pressure, volume work, and so pressure we find is force divided by area. So the units of force divided by some sort of square distance. But volume is distance cubed. Pressure times volume is a work term, kind of like in a piston, and we can use that to calculate work. So if work equals force times distance, we can say, well, we can get that from pressure volume because pressure times change in volume is equal to force divided by distance squared, and volume is distance cubed. All but one of those distances cancel in the mathematics. We find that force times distance equals work. If we take dry ice, put it in a sealed bag, we allow that to sublime. Since it's sealed in the bag, it can lift the book and therefore do work. If we use our ideal gas equation, which we'll talk more about in the gas law chapter, we can look at changes in the number of moles of gas and in the change in the volume. So PV equals nRT, so P delta V equals delta nRT. So I can express the work term not only in terms of change of pressure and volume, but in change of moles of gas if I just had a balanced reaction, where delta N is the change in number of moles of gas over the course of the reaction. So work is force times distance, which equals negative P delta V which is equal to negative nRT. We assume the pressure and the temperature are constant, where R is the universal gas constant, and we'll work that into a problem, and so you'll get the value of it. If we look at this question, so just signs of the work and the heat, the sign conventions, if it's going into the system, work or heat, that in the left column, work done on the system or heat going into the system is positive. Work done by the system on the surroundings or heat leaving the system are going to be negative. So let's look at this next question. Balloon is heated very slowly, absorbs 500 joules of heat. It expands against a constant pressure in the atmosphere, 101.3 kilopascals, and expands by a volume of 3.46 liters. We want to calculate the change in the internal energy, and we'll need our work formula to do that. All right, let's take a look at this particular problem. Now, what we can see is we copied things over. We got 500 joules of heat being absorbed by the system, so it's positive. 101.3 kilopascals. We're going to have to do something with that unit to make it work out. And then 3.46 liters. We're going to need to do something with that as well. Now, what we found for the pressure is pascals of pressure are newtons per square meter. If it's a kilopascal, then it's a kilonewton per square meter. If you do kilonewtons per square meter, you get kilojoules instead of joules as far as the units go. And so we're going to say that that is equal to 101.3 kilonewtons per meter squared. Now, to get the volume, we're going to put in our conversion factor. There's 1,000 centimeters cubed per 1 liter. That's just a basic unit conversion. Then we have to cube the conversion factor, so per meter cubed compared to centimeter cubed, there is 100 or 2 squared centimeters or centimeters in 1 meter. So we have to cube that, so it's 10 to the 6th centimeters per 1 meter. When you do that, you get 3.46 times 10 to the negative 3rd meters cubed. Now, we need that, but that's not our final answer. Remember now, our work term is negative P delta V. So if we go for our change in internal energy, heat plus the work, so that's going to be a positive 500 kilojoules minus 101.3 kilopascals. So then we got to do 3.46 times 10 to the negative 3rd meters cubed. And that's not going to change the amount much, so it's still approximately equal to 500 kilojoules, which shows in many chemical reactions end up like this, the amount of work, if it's open to the atmosphere, ends up being a negligible amount. So in this chapter, we end up focusing a bit more on heat than the heat and work. We can predict what's going to happen with the work based on the change in the volume and looking at some example reactions. For example, if the volumes are equal, then P delta V is 0, regardless of what P is. Change in moles of gas has to be 0 then. So there's not really any work done. Carbon dioxide plus water, there's 2 moles on the reactant side, yields hydrogen gas and CO2, 2 moles on the product side, they're equal. That's going to net no work. And then if the second volume is bigger than the first volume, then I'm doing work on the surroundings. P delta V is positive, delta N is positive. I got no moles of gas on the reactant side, zinc and HCl, but I liberate some hydrogen. So, hey, that reaction can push out and do work on the surroundings. If the second volume is less than the first volume, then P delta V is negative, delta N is negative. Something like nitrogen plus 3 hydrogens, that's 4 moles on the reactant side, forming 2 moles of ammonia on the product side. Reduction in number of moles, so the system does work on the surroundings. Now, if we consider the following gas phase reactions at constant temperature and pressure, using that information to determine if work's done on the system, on the surroundings, or if no work is done. So if we look at this first reaction, we see we got 2 moles of NO, 1 mole of oxygen. That's 3 moles on the reactant side, only 2 moles on the product side. That is a reduction of the volume. So V2 is less than V1. So that means work is done on the system. In this second one, you can see that the moles of gas are the same on both sides, 2 moles on the reactant, 2 moles on the product, so no work is done. This last one, I have more moles. I got 1 mole on the reactant side, 2 moles on the product side, so an increase in the number of moles of product versus the reactant. So in this case, V2 is bigger than V1, so that means it pushes out and work is done on the surroundings by the system.